With this morning's session. Our first talk will be a lecture on Introduction to Numerical Relativity, and it will be delivered by Carsten Gundlach. Carsten is a professor at the University of Southampton, and his focus is critical collapse. He shared his lecture notes, and you can find it from the website. You can download it from the program session if you didn't do it yet. Carsten, you have 45 minutes, and our schedule actually is very tight.
Yes.
So I'll let you know when you have 5 minutes left before the questions. So
Okay.
after you start, after 35 minutes, you start. Okay. You
Okay.
can start whenever you're ready.
Thanks everybody for giving me your time. I hope you find this useful. I tried to cover quite a lot, so I thought I'd share my notes so that if I have to go a bit fast or if something doesn't fit at the end, you have a complete version. So I want to spend most of the time trying to derive how we can do the notion of starting with some three-dimensional initial data on a hypersurface of constant time, sigma 0, and then evolve to future hypersurfaces, sigma t. So we want to have something that is essentially coordinate invariant, three-dimensionally geometric, but with a time foliation. And getting that from the ordinary space-time picture is a little bit intricate, so I'll try and focus on what I think are the essential steps. First of all, if we just have a time function t, then we can find its gradient, which in geometry notation is like that. That's a gradient, and that means like the partial derivative. No covariate derivative required here. And if we have any vector that is tangential to one of those hypersurfaces, then that inner product here of a vector and a covector will be 0. What that's saying is that if we move inside a surface of constant time, then obviously the time doesn't change. And that's what it means that VA is tangential to the surface. Now, I have introduced a time coordinate. I will not introduce space coordinates yet. I want to do that separately for pedagogical purposes. But I will now introduce the metric and the covariate derivative. So if I have that, then I can make a unit normal vector. And now I can use the gradient operator to express the Nabla operator to express the gradient. Of course, with indices downstairs, it comes to the same thing. And then I can raise that thing. By the way, if I write colon equal, I mean I'm defining something. And I'm enforcing that this thing has length -1. So the -1 is because it's time-like. The -1 here is so that it's future pointing towards increasing t, and alpha is obviously defined from that normalization condition. Okay, the next thing is I can introduce something which will serve as a metric on the surfaces of constant t, and also as a projection operator into these surfaces. So I'm defining this object, which is still a four-dimensional object, but in the end we will see that it's really three-dimensional. And here again, the plus sign is because I'm using a vector n, which is time-like. And from that, one can verify, and you can maybe do this in your head, but if else it's not, it's one line. We have NA into HAB is 0. And also, if we use the metric to raise and lower indices, so in the following up, when I raise and lower indices, I will always use the space-time metric. So if I have this object with one index up and one index down, and I contract it with itself, then I can think of that as a matrix product. And this is saying that the product of a matrix with itself is the matrix again. And in that sense, it is a projection operator. So a projection operator is a linear operator that obeys P star is equal to P. But I will actually call this operator perp. So maybe instead of P, I'll change my mind. I'll call it perp. Sorry. P is just the usual symbol for a projection operator. So what it is that the projection operator goes from goes from the tangent space of a space-time to the tangent space of sigma t, and similarly it goes from the cotangent space of a space-time to the cotangent space of sigma t. So in other words, if I have an object with indices downstairs, then I can use that to get contracted with that operator perp, which is h with one index up and one index down. And if the indices are down, I can do the same thing. And we have seen that is a projection in the sense that if we do it twice, we get what we had in the first place. And so we can say that a tensor T is spatial. Sorry, it's harder to write on the white on a board. If and only if, and I'm defining again, the projection of the tensor on all its indices is equal to the tensor. So, for example, HAB itself is spatial. And so if I have VA and WA spatial, then it means that contracting them with the metric, the space-time metric, is the same thing as contracting them with HAB. And so in that sense, HAB is the restriction of G to the tangent space, to the metric on the tangent space of sigma t. Okay. So because H is itself spatial, if I have any spatial vector, it doesn't matter if I raise its indices with G or with H. So in some sense, quite often it doesn't matter when I raise and lower indices if I do it with H or G, as long as the thing itself is already spatial. Now, the next thing is I want to introduce time derivatives. Now, you would think of this being the vector partial t, d by dt, but that depends on the coordinates xi. So if I have a coordinate t and I also have coordinate xi, then partial t means I take a derivative with respect to t at constant x. But if I haven't introduced the x yet, I can't do that. So we haven't got that yet. What we can do is we have the lead derivative along n. And so I can define k to be minus 1/2 the lead derivative along n of HAB. So first thing to note is that the minus sign is a convention. There are two conventions, and they're both equally frequent. So I've chosen the convention that is the one in the book by Baumgart and Shapiro, which you may want to use. But if you ever consult Wald on this, he has the other convention. And one can show that this is also equal to, this is not completely obvious, but it's a calculation one can do. It's the projection of del A NB. In what sense it is that it is a time derivative, we will see later. But in some sense, it is it's a lead derivative with respect to a vector that's time-like. Okay, so I now have some notion of a time derivative of the 3 metric, and I want to use that in a moment to formulate the ADM equations, but I also need a notion of a spatial covariant derivative. And when you do numerical relativity, you have a free metric, and then you would calculate, for example, the covariant derivative in space by using the Christoffel symbols in the three-dimensional space. You might calculate the three-dimensional Riemann and Ricci tensors from that. And that's all very good, but there's a really nice shortcut if you start in 4 dimensions. So we define that the spatial derivative of some tensor, and this has to be a spatial tensor, or if not, we make it one. So this is spatial. Sorry, when I said we make it one, I misspoke. This is spatial. Well, that is defined to be just the projection of this derivative. And it's worth stressing that this is nabla A, TBC, and so on, is a tensor which has one index down more than T itself, and it's a tensor, and it's not going to be spatial unless I project it. So in particular, even if, say, B takes a spatial value, say 1, 2, 3, it's not 0, then after I've taken the derivative, then that won't necessarily be 0. So I have to project every single index. And from that, it's really easy to see that DAHBC is 0. So that's a very easy calculation to do. Almost you can do it in your head. If not, it's one line, but I will not do any calculations here. And then the amazing thing is that we know that a covariant derivative is unique for a given metric if we assume that it is torsion-free. So dA is unique if we assume no torsion, which is what we want to do in relativity. So that means that you could very laboriously work out that if we calculate the three-dimensional Christoffel symbols from the four-dimensional Christoffel symbols, and then we actually just see that by taking the definition of HBC and the definition of D, and it's a one-liner. Okay, so let me maybe pause here. And well, when I gave this talk in Southampton for a practice, I asked people if people had questions. I don't know if that is easily possible here, but if somebody has an urgent question, then maybe they should switch on their microphone and ask it now, because it would be helpful. Okay, if not, I'll go on. Maybe I'll switch to a fresh page. So now we introduce the full space-time coordinates. And in the end, I will take them away again. But let's introduce them first. So we have space-time coordinates t and xi, and so now we have a partial derivative as well. And so in these coordinates, we have that n mu is minus alpha 0, 0, 0. That was just what I said earlier, that NA is, in geometric terms, is minus alpha nabla A T. Okay. So if T is spatial, then T with any indices up contracted with NA is 0 by definition, but that's equivalent to saying that the only thing that we can contract with, if we now expand this in coordinates, so let me take them, turn the A into a mu, so that we now have a sum over coordinates. So I'm using the Wald convention where A, B, C are abstract indices and mu, nu, and so on are concrete indices. So this tells me that T with a 0 here, and any indices elsewhere must be 0. So that's already worth knowing that if we have coordinates t and x, then any t component of upstairs component of any tensor that's spatial must be 0. Okay, so now before we had that for any spatial vector, so spatial vectors would be purely space-like, right? And from that, E spatial. And from that, we know when we looked at VA, WA, GAB is VA, WB, HAB. That now tells me that GIJ is equal to HIJ. And this is for I and J, sorry. I and J from 1 to 3. So the other thing is that I know that H0I must be 0. And, oh, sorry, I forgot now. I forgot to use something. I've made a very small change to the order with respect to what you've seen. So from what n mu downstairs is, we want that n mu upstairs is equal to, the first component must be plus alpha to the minus 1, and the rest of the components are not specified from the fact that n is has unit product with n downstairs. So I will now introduce something which I call alpha to the minus alpha to the minus 1 beta I. And if you look at this like that, it's a rather odd convention to have the minus alpha to the minus 1 in front and call these components then beta I. But let me do that. So let me define that. And now I'll come to what I wanted to say, namely that we have that H0I is 0. If I express that in terms of n up and GAB up, then I'll find that G0I up is equal to minus alpha to the minus 2. And then similarly, from H00 up, which must be true because it's a spatial tensor, I find that G00 up, I'm sorry, I miswrote here. It's minus, I got confused. That's a vector. And that is minus alpha to minus 2. So it all looks incredibly messy. So now I have a relation between all the components of G, but 6 are downstairs and 4 are upstairs, the components of H, and then these 4 additional quantities, alpha and beta. And alpha I had previously defined geometrically. Beta is just going to be, if you like, a shorthand for G0I up. And now I have a relation between an expression for G mu nu up and G mu nu down, but they're both incomplete. However, if I want that they're inverses one of each other, then I can work out what everything should be. And it's quite complicated, and this is the only formula I need to really look up. I can never quite remember it, but it works out like that. Okay, so again, it looks really complicated, but I'm sorry, I keep correcting something, sorry. This is what I meant to write with a minus here. And then similarly, the downstairs metric is that. And here, of course, I've contracted beta with itself. I've raised and lowered these indices with either G or H, which doesn't matter. And so basically specifying that we have Gij down is given, G0I up is given, and G0 up is given, and that these two things are matrix inverses one of the other, that gives me the complete picture. And then the thing that I do know by heart is how we can write the downstairs metric, and it looks very much more satisfactory. It's minus alpha squared dt squared plus Hij, and now we have dxi plus beta I dt times dxj plus beta j dt. So of course, everybody has seen that, I would imagine. But I always found it confusing to see where that came from when I read sort of standard introductions. And so here is sort of my personal answer to where that comes from. Okay, let me pause here again and see if there are any questions. Right, then I'll move on. So we now have partial is a vector. Let me call that TA. So remember that this vector depends on the spatial coordinates, not just on t, because the spatial coordinates tell us what partial d by dt actually means. And so the upstairs components of that are 1, 0, 0, 0 from the definition. That's just a partial derivative. And then from the formula I just wrote for n, which was, if you like, the definition of what the betas are, but now we know what they are in terms of the metric. From that, it follows that covariantly, we can write TA as alpha NA plus beta A, where I've now turned beta into a 4-dimensional vector. So obviously with components, beta mu is 0, beta I. But this formula is really important, because working in coordinates for a little bit, namely I have introduced the coordinates I, and I don't really know an elegant way of not doing that. But we now have this geometric relation again between these three vectors. And here, of course, is the famous picture that you've also seen. So we have, if I draw this in one space dimension, here is sigma 0. Here is another surface, sigma t. So if I want to say how far away are these two well, let me call it delta, let me call it dt, because I really want to make it infinitesimally close. So the first thing is, what's the distance in some sense between those surfaces? And specifying that is the law of alpha. And then the second thing is, what are the coordinates on each surface? So if I have points of constant x here, then what should be the same point up here? Say it's those points. So now I have this vector, and this vector by definition is TA. So that's the saying this is how I move at constant spatial coordinate in the time direction. But I can now express that as the normal vector times alpha, and then going sideways in a purely spatial direction, and that is beta A. So that's the and if I wanted to clutter up this picture even more, that I could draw the vector NA here, right? So the vector NA has a fixed length. So that's a picture probably everybody has seen. And again, when I first saw it, I said, yes, it's very good, but why would we make this definition? whereas I think the way I've derived it, it's more satisfactory to me. Okay, now the next thing is again a little bit subtle, and that's something I think is not really made very clear in the standard textbooks that I'm aware of. And it's just a very small point, so I'm sorry, I didn't mean to do that. I meant to start writing in black again. So if I have some three-dimensional tensor, or spatial tensor, I should say, then let me define t dot to be the partial derivative of t. These are all definitions. And by partial derivative in a coordinate system, I really mean the Lie derivative. So the Lie derivative with respect to some vector which is a coordinate basis vector is just the partial derivative expressed in coordinates. And so I now can take the definition of t. So that's equal to L times alpha n plus beta. Maybe I should remove the index here and go index free, but that's a vector. And that's, of course, here's at the bottom. That wasn't very clear, sorry. T. And from the linearity of the Lie derivative, this is Lie alpha n t plus Lie beta t. And there's now a little bit of things that is often missing, which is that's something you can work out directly by working in coordinates. Lie alpha n of a purely spatial tensor, which has indices down only, like the metric or like the extrinsic curvature with indices down, that actually is alpha times the Lie derivative along n of t, again with indices down. And so the first example of that is that hij dot is equal to minus 2 alpha kij plus Lie derivative along beta of hij. And here, everything follows directly from definitions I've made previously. But the fact that the alpha here comes out, that is just this previous line. So that's the only bit that is not obvious from the previous definitions. Okay, and then one can show from the Einstein equations now. I take the Einstein equations, and for simplicity, I'm putting myself in vacuum. If I take the Einstein equations with indices down and I contract them all indices, then one can show, and this is a very long calculation that I cannot attempt to do, but for example, you will find it covered in Wald. So ki dot, in the same sense, that is now, and I'm writing this out because it's worth seeing, but it's something that I, again, have not memorized, so I need to copy it. K is the trace of Kij. So, and this is the three-dimensional Ricci scalar. So this is really an identity about decomposing the four-dimensional Riemann tensor in terms of the three-dimensional Riemann tensor, and then working out what this object on the left here is. And then there is this thing. And where that comes from, again, that is quite intricate. That comes from the fact that I can think of derivatives of n to be second derivatives of alpha. So this is a derivative of n. So this is like an extrinsic curvature thing here. And then I have the term that you would expect, which is that. So that's exactly the same thing. There's a term, a Lie derivative term you have here. So I want to stress that this first thing is just a definition or combination of the definitions, where this is the decomposition of the three-dimensional Riemann tensor with respect to the four-dimensional Riemann tensor. So we can write the four-dimensional Riemann tensor plus lots of other things. And that's where this comes from. And I'm writing the components here. And then the other things are the other components of the Einstein equations. So if I contract with n once and project the other index, then that gives me that dj kij minus di kij. Sorry, dik, sorry. That is 0. So this, of course, is just a divergence. And that's 0. And then if I contract GAB, the Einstein equation, with n twice, then that gives me the Hamiltonian constraint. No, there's a minus here. And for simplicity, as I said, I'm not putting in the matter terms just so that I don't have to write them down. And so then we have these 4 equations. Now, here comes a bit that I will just say in words, but it's really important. I've written indices ij here, and you may wonder what the status of that is. So I can do this calculation in components. However, I can also think of this as being an expression or 4 equations which take the 3-dimensional tensors hij and kij and the covariant derivative with respect to hij. And then also I have this additional thing, dot. And so I've just made definitions of of what dot is. Namely, dot is this definition here. So that means that I go outside the 3-dimensional space, this 3-dimensional time slice, because I have to introduce this definition, these derivatives outside. But then it turns out that I can write this, the dot acting on hij and then kij, in terms of purely spatial tensors. So that means that hij dot is actually transforms as a spatial tensor and kij dot transforms as a spatial tensor, because everything on the right by definition is a spatial tensor. It will transform as a tensor. We have defined that k is a tensor, the d is a partial derivative, and so on. So in this case, I can think of these equations, these indices ij, either as coordinate indices, and that's of course what you do in numerical relativity when you do calculations in coordinates, or else I can think of them as abstract indices, but with respect to the 3-dimensional manifold sigma t. But then of course I need the derivatives outside that manifold, which I've sort of introduced by hand by introducing space-time coordinate. But now I can withdraw the space-time coordinates except for the time slicing and be abstract in space again. Okay, so I've now got like 11 minutes left. So I will not be able to finish, I think. But let me go on. And now let's talk a little bit about well-posed formulations. So let me say write as little as possible because that slows me down. And everything I'm saying is pretty much in those notes. So we have a PDE problem is a PDE, like the Einstein equations, with certain boundary and initial conditions. For example, we could think of specifying hij and kij on the initial surface sigma 0, and then we evolve and we specify alpha and beta freely, saying, okay, we build the coordinate system as we go along. The picture of that we have seen previously. And it turns out that doesn't work for numerics. And it turns out that doesn't work for numerics because it's actually an ill-posed PDE problem. And so the notion of a well-posed PDE problem is crucial. So a well-posed PDE problem is one that has a solution, and the solution is unique. Well, that's not problematic for the ADM equations. And the solution should depend continuously on the data. For example, Hij and Kij, and the choice of alpha and beta. And it should depend continuously in the following sense, that I have some function norm of a small variation of the solution. So I'm effectively linearizing here. And there's another function norm. By the way, this approximately equal should be approximately less similar should be less equal here in my notes. That's a typo.
Carsten, you have 5 minutes left.
5 minutes?
Yes.
Oh, for questions.
Yes,
Yes.
for
Okay.
questions.
Well, then I will. Right. Good. Then I will just abruptly stop somewhere. But let me finish right here. So we have two function norms, and we have some change in the initial data, and we have a change function norm on the change in the solution, and they should be related in this way. And what goes wrong with that in ADM or in any other ill-posed problem is that if we make a small change to the data and we make that arbitrarily high frequency in space, so make it arbitrarily quickly varying, then the change in the solution grows arbitrarily rapidly in time. And that means I can't have such a bound. And the way of getting around that is to obviously find a different formulation of the Einstein equations. Now, a formulation, again, I'm saying it in words, a formulation of the Einstein equations is what combination of what 6 equations of the 10 Einstein equations do I actually use, or what 6 linear combinations of the Einstein equations do I use? So in ADM, I use the projections into space, but I impose the other ones only on the initial data. And of course, that's compatible. In the continuum, the constraints are propagated by the evolution equations. But the choice I make, I can add the constraints to the evolution equations, and that will give me a little different combination of equations to use. Then I can choose the gauge. I can choose alpha and beta in different ways. And also I can introduce additional variables. For example, I can reduce to first order in space and time. That gives me lots of additional variables. And then their definitions are constraints, which again must be imposed initially and which then I can add to the right-hand sides. And that gives me a lot of formulations to play with. And how can we see if a formulation of the Einstein equations will give rise to well-posed problem? Well, there is a necessary condition that the formulation has certain algebraic properties, which are either that the solution, that the PDE problem is strongly hyperbolic or symmetric hyperbolic. And there is a lesser algebraic property of that is weakly hyperbolic. And strongly hyperbolic, symmetric hyperbolic implies strong, and strong implies weak, and weak is not good enough. So if we have weak, we have that everything propagates at finite speed, but we can't get this continuous dependence. Whereas if strong and symmetric hyperbolicity, we can find ways of making well-posed initial value problems given a formulation of the Einstein equation that's strongly or symmetric hyperbolic. Okay, now will I just completely stop and leave you with the last page or so of my notes to read in your own time, where I'm talking about 3 well-posed formulations, namely the generalized harmonic formulation, the Z4 formulation, and the BSSN formulation. But I think I'll just stop here because everybody hates lecturers overrunning. Thank you.
Thank you very much. Thank you very much, Carsten, for the very nice lecture. So if anybody has a question, they can raise your hand or write from the chat.